Hello, and welcome back to the FUNWAVE application on the ERDC HPC portal. In this tutorial, we'll be moving to the fourth tab of our simulation workflow, the Run tab, where we will go over reviewing your inputs and submitting a job. This is the 9th video in our FUNWAVE application video tutorial series. Be sure to check out previous videos to catch up on the other components of the simulation workflow. As always, tune into the FUNWAVE comprehensive wiki page to learn more about the model and its input parameters. So, if you've ever used FUNWAVE before, you're familiar with the driver or control file called input.txt. In newer versions of FUNWAVE, you'll be able to customize the name of this control file when using a terminal to submit jobs. In this HPC portal application, in principle, it's meant to eliminate the need to interface with the terminal to run FUNWAVE. However, if you are a more advanced user and are comfortable with the original input.txt format, you can review, edit, and add to the control file here at your own risk, of course. So recall from the physics and numerics tutorial, we mentioned the possibility of modifying the numerical scheme of the default runch-kutta to a different scheme, or from the wavemaker tutorial, the possibility of using a left boundary wavemaker instead of an internal type wavemaker. You'd be able to do that here if you know what you're doing and how to set that up. Otherwise, this window provides a general overview of your simulation as it was built in the previous tabs, from the Input-Output tab and the Bathymetry Topography tabs. And it's formatted in the form of the input.txt control file, nicely spaced out here. You do have the option to edit this input file directly, but please do so at your own risk. There are some extra default parameters, settings, and values that you'll actually see in this file that were not directly an option in the application on the previous tabs. So for example, if we scroll to the numeric section of this file, we see that the time scheme variable and related parameters are shown here that were not available in the previous tab. If you are an advanced user and you'd like to change these default options, you may do so, but please review the wiki to double check that your input variables and values are correct. These variables are case sensitive, so please take care when editing these variables directly. Now, any changes that you make in this window will overwrite the options that you selected from the previous tabs. To revert the input file back to the options selected into the application from the previous tabs, you can click this Generate Input File button to essentially reset this input file. Now, you can edit this file in two ways, either by selecting this Edit button in the Input Scroll window, or by typing your additions in this Additional Inputs window below. Now, this window does come with a warning that any additions you provide will not be checked or saved in the application before running. This additional inputs section is particularly useful when there are new developments in the FUNWAVE code that have yet to be implemented in the portal application itself. So say we haven't been able to create the updated fields yet in the portal, but the latest code of FUNWAVE is available on the HPC. In that case, you would be able to add the relevant parameters specific to that new feature in this window to include in your input file. In the next section below the input file window is where you will set up your simulation to be executed on our ERDC HPC machine, Onyx. The first parameter is the time of the last run, which is not applicable for new simulations like this one, but if you had run the simulation before, it would update that time. Below that is the wall time field, which is the amount of time you estimate this simulation will run for on the machine. This is different from the total time of your simulation. The total time is how long in physical time the simulation will propagate waves, while the wall time is how long the model itself will take to run that simulation. The wall time depends on the total size of your grid and how long the simulation will propagate waves, so your total time. A higher wall time is recommended for larger grids and longer wall times, or longer total times rather. Additionally, this wall time is related to the queue selection. The maximum allowable wall time will vary depending on the queue you choose. For example, in the debug queue, the maximum available wall time is 1 hour. This queue is mainly used to test or check the stability of your simulation. Anything greater than 1 hour in this queue will return an error on the HPC. If your job requires more than 1 hour of wall time, it's recommended that you select the standard small queue. In this case, the standard priority small jobs queue. This queue is good for 24 hours of wall time, which most simulations should complete well within 24 hours, again, depending on the size of the domain and total time of the simulation. For more information about these queues available on Onyx, the info icon here will direct you to the users page of the ERDC HPC. So let's click on that. And here we have some information about our high performance computing systems available at ERDC. For this portal application, we'll be using Onyx, and we can navigate to this queue summary link here to review the job names as well as the maximum available wall time for each queue. Ultimately, we do recommend selecting the standard small queue for your applications here. Jumping back to the portal. Now, recall from the temporal specifications tutorial, we were generating a simulation that required at least 50 cores, which was the product of our px and py variables, or the number of cores in x and y respectively. In that example, we would select 2 nodes here, totaling 88 cores to cover the resources we would need for that job. In requesting a total of 88 cores, but only needing 50 cores to run the simulation, there would be 38 cores that were allocated on the HPC that would not be used for this simulation. So you could adjust the total number of cores in X and Y, or the PX and PY variables in that temporal specifications field of the Inputs tab to be a multiple of the number of cores per node available on Onyx. For example, this PX could be adjusted to 11, and this PY could be adjusted to 8, and the product of these variables would define how many total cores or processors you would need to allocate for this simulation. So in this case, that would be 88 if we did change these, and that would use 2 full nodes on Onyx. This is just an option to consider since you would already be allocating 2 nodes to meet the original 50 processors needed for this simulation. So you might as well reap the benefits and the processing power of all the cores on each node requested. For this specific example, we are going to stay with a PX of 2 and a PY of 1 here for a total number of cores of 3. This is a smaller simulation than what we were going through in the previous tutorial. So along those lines of selecting an appropriate number of cores per node and the total size in PX and PY, how many resources to allocate, there is a logic to selecting an efficient number of cores or processors in X and Y and the total number of resources you would need on the HPC. The optimal number of cores for any given simulation really depends on the specific grid size and setup, so it would be job specific. If you're interested in learning more or have questions about the optimal configuration for your simulation on the HPC, feel free to reach out to us via email, either directly or using this expert help and bug reporting option. Again, for this example, we're going to stick with a PX and a PY of 2 and 1. So we would only need to request 3 cores. And so we only need to request 1 node on Onyx. Now, if you've been following along with these tutorials, you most likely already have access to the portal and have an account set up under the FUNWAVE allocation on the HPC. You would select that account identifier here. In this case, I'll select this one. Now, with all of these options filled in, you're ready to submit your job to the queue. In the queue, the simulation will wait until the resources you requested are made available, and only after that will your simulation begin running. Now, once you select this Run Simulation button, the portal will send the simulation to the HPC and a loading screen will appear. Now, if your simulation was successfully placed in the queue, this page will update as you see here. The portal will periodically check the status of your simulation with the HPC and update this text accordingly. So on the home screen of this application or your sandbox, you'd be able to see an updated status of where your simulation is, whether it's in the queue, if it's new, if it's running, is it finished? And once it is finished, you'd be ready to view or access the output files in that 5th tab of your workflow, the post-processing tab. Or you can download the output files directly to your local machine from the ERDC HPC Portal page. Now, once a simulation has finished, you can view the standard output and error files associated with your simulation. And this can be found at the bottom of your Run tab. So you have a little update on the bottom here, specifying your results and where to find them. And you can view the simulation and standard out and standard error files here. These files tell you a bit more information if there was an error at any point in running your simulation, and if so, at what time step the error occurred. So if your simulation was successful, you can move forward to the 5th tab, the post-processing tab. And we'll cover that tab in the next video. So with that, this concludes our tutorial on the Run tab, the 4th tab in our simulation workflow for the FUNWAVE HPC Portal application. We do hope that this has been helpful. Check out the FUNWAVE Wiki or the ERDC DSRC webpage for more details on the information discussed in this video. If you do have any other questions, please reach out to us via email or join our mailing list. Happy modeling!